Photons, the fundamental particles of light, exhibit behavior that challenges our classical understanding of physics. Unlike the deterministic nature of classical mechanics, where the future state of a system can be predicted with certainty, if its current state is known, photons operate under the principles of quantum mechanics. This shift from classical to quantum thinking represents a profound change in how we perceive the universe. One of the most striking demonstrations of this is the famous double-slit experiment. When photons pass through two slits and onto a screen, they create an interference pattern typical of waves, not particles. This pattern suggests that each photon interferes with itself, traveling through both slits simultaneously. This wave-particle duality is a cornerstone of quantum mechanics, illustrating that particles like photons can exhibit both particle-like and wave-like properties depending on the experimental setup. But here's where it gets even more intriguing. When we try to observe which slit the photon actually passes through, the interference pattern disappears. The act of measurement collapses the photon's wave function, forcing it to choose a definite path. This phenomenon underscores a fundamental principle of quantum mechanics, the observer effect. The mere act of observation changes the outcome, blurring the line between observer and the observed. Heisenberg's uncertainty principle further illustrates the loss of determinism. It states that we cannot simultaneously know both the position and momentum of a photon with arbitrary precision. The more accurately we know one of these properties, the less accurately we can know the other. This intrinsic uncertainty is not due to any flaw in our measurement instruments, but is a fundamental property of quantum systems. This principle is not just a limitation of our measurement tools, but a fundamental characteristic of reality itself. In classical mechanics, if we know the initial conditions of a system, we can predict its future state with certainty. This is determinism. In contrast, quantum mechanics introduces probabilistic outcomes. Even with complete knowledge of a photon's initial state, we can only predict the probabilities of its future states. This probabilistic nature of quantum mechanics challenges our intuitive understanding of the universe, which is based on cause and effect. This shift from determinism to probabilism doesn't just apply to photons, but to all quantum particles. It represents a fundamental change in our understanding of the universe. At the quantum level, nature behaves differently than our everyday experiences would suggest. This leads to a range of counterintuitive phenomena, such as entanglement, where particles can instantaneously affect each other regardless of distance, and superposition, where particles can exist in multiple states at once. Great minds like Albert Einstein and Niels Bohr debated these concepts. Einstein famously said, "God does not play dice with the universe," expressing his discomfort with the randomness inherent in quantum mechanics. He believed that there must be hidden variables that we have yet to discover, which could restore determinism to the quantum world. Bohr, on the other hand, embraced this indeterminism, arguing that quantum mechanics provides a complete description of nature. He suggested that the probabilistic nature of quantum mechanics reflects a fundamental aspect of reality rather than a gap in our knowledge. The philosophical implications of these debates are profound. They touch on questions about the nature of reality, the limits of human knowledge, and the role of the observer in shaping the universe. Quantum mechanics forces us to reconsider our place in the cosmos and the nature of existence itself. Today, the implications of photons and the loss of determinism are foundational to modern physics, influencing fields from quantum computing to cryptography. Quantum computers, for example, leverage the principles of superposition and entanglement to perform calculations that would be impossible for classical computers. In cryptography, quantum key distribution uses the principles of quantum mechanics to create theoretically unbreakable codes. While we may never fully grasp the bizarre behavior of the quantum world, its mysteries continue to inspire and challenge our understanding. The study of photons and quantum mechanics opens up new possibilities for technology and deepens our appreciation for the complexity and wonder of the universe. Thank you for joining us on this journey into the quantum realm. Stay curious, and until next time, keep exploring the wonders of the universe.